orthogonal transformation. Find the orthogonal transformation which transforms the quadratic form x1 square plus 3x2 square plus 3x cube square minus 2x2 x3 to the canonical form. First, we have to write this quadratic form to the symmetric matrix. That is the first step. Given quadratic form is x1 square plus 3x2 square plus 3x3 square minus 2x2 x3, where a is equals to, so this is the place of your x1 square. So what is the coefficient of your x1 square? It's a 1, and this is the place of x1 x2. There is a no x1 x2, so this is going to be 0, and this is the place of x1 x3. There is a no value, it's a given of x1 and x3, so this is also 0, and this is the place for your x2 x1. No, there is a no value for x2 x1, and this is the place for your x2 square. What is the coefficient of x2 square? It is a 3. And next, this is the place for x2 x3. So that value, it's the coefficient of that value is equals to minus 2. That should be divided by 2. And next, this is the place for your x3 x1. There is a no x3 x1, so it is a 0. And this is the place for x3 x2. So x2 x3 it's given, that value we can utilize for x3 x2 also. So minus 2 by 2, and this is the place for your x3 square. X3 square coefficient, it's equals to 3. So the given first step, it's got completed. We have written the given quadratic equation into the symmetric matrix, where a is equals to 1 0 0 0 3 minus 1 0 minus 1 3. Now next step, we'll move for finding the eigenvalues. For finding the eigenvalues, what we have to do? We have to find the characteristic equation, where the characteristic equation mod of a minus lambda I, which is equals to 0, mod 1 minus lambda 0 0 0 3 minus lambda minus 1 0 minus 1 3 minus lambda, which is equals to 0. So now what we are going to get? 1 minus lambda of 3 minus lambda minus 1 minus 1 3 minus lambda, it's equals to 0. So 1 minus lambda of 3 minus lambda 3 minus lambda, minus minus into minus, it's a plus, and outside minus, it's a minus 1, it's equals to 0. 1 minus lambda of 3 into 3, 9 minus 3 lambda minus 3 lambda, then plus lambda square minus 1, which is equals to 0. 1 minus lambda of lambda square minus 6 lambda plus 8 minus 1, that will give you plus 8, which is equals to 0. 1 minus lambda, which is equals to 0, or lambda square minus 6 lambda plus 8, it's equals to 0. 1 minus lambda, it's equals to 0. Lambda is equals to 1. And next, this 1, Here the constant is equals to 8. So this 6 we can split, minus 4 and minus 2 we can write. That is known as a common factors. With the help of a common factors we are finding the values. So lambda square minus 4 lambda minus 2 lambda plus 8, which is equals to 0. Lambda of lambda minus 4 minus 2 of lambda minus 4, which is equals to 0. The common from this, it's lambda minus 4. Lambda minus 4 of lambda minus 2, which is equals to 0. Lambda minus 4 is equals to 0, or lambda minus 2 is equals to 0. So lambda is equals to 4, lambda is equals to 2. So we got the eigenvalues is equals to 1, 2, 4. We got the lambda values. Lambda, it's equals to 1, 2, 4. These are known as eigenvalues. Eigenvalues. Once we'll get the eigenvalues, we have to move for finding the eigenvectors. First case, we'll move for finding, that is the next step, we'll move for finding the eigenvectors. First case, lambda is equals to 1. Case 1, when lambda 1, it's equals to 1. Therefore, a minus lambda 1 into I into x1, it's equals to 0. There, what was our matrix? That is 1 minus lambda. So 1 minus 1, 0, 0. Next is 0. 3 minus 1, minus 1, 0, minus 1, 3 minus 1, which is equals to 0. Now here what we are going to get? 1 minus 1, 0, 0, 0, 0, and this is equals to 2 minus 1, then 0, and this is equals to this is equals to minus 1, and this is equals to 2 x1, x2, x3, x1, x2, x3, which is equals to 0. Now what we are going to do here? See, the first row completely it's equals to 0, and this is an identical one. We cannot proceed for going for the statistical equation also. So in that case, we'll make this is equals to 0 and see what we are going to get. Your R2 R2 tends to R2 2R2 plus, sorry, it should be R3. R3 tends to 2R3 plus R2. In that case, it's a 0, 0, 0. This is equals to 0. 2 minus 1. This is equals to 0. Minus 2 plus 2, 0. 2 into 2, 4. 4 minus 1, it's equals to 3. x1, x2, x3, which is equals to 0. Now what your rank here, it's equals to your rank of A, it's equals to 2, and the solution is going to be number of unknowns minus rank of A, where unknowns is equals to 3, 3 minus 2, it's equals to 1 solution. First write this into the equation form. 2x2 minus x3. 2x2 minus x3, which is equals to 0. 3x3, which is equals to 0. From the last equation, this is equation 1 and this is equation number 2. From equation number 3, we are going to get x3 is equals to 0. From equation 2, x3, which is equals to 0. And from here, we will assign some arbitrary value. So, we will take let x3, we are having x2, then we will assign x1. Let x1, it's equals to k. So what we are going to get here, 2x2 minus x3 value is equals to 0, x2 is equals to 0. So what is your first vector? x1 it's equals to x1, x2, x3, which is equals to k 0 0. So which is equals to k of 1 0 0. Next we'll move for the next case, that is lambda is equals to 2. Case 2, when lambda it's equals to 2, a minus lambda 2 into I into x2 it's equals to 0, where that matrix, so what we are going to get, that is equals to 1 minus 2, 1 minus 2 0 0, next is 0, 3 minus 2 minus 1 0 minus 1, then 3 minus 2, which is equals to 0, x1, x2, x3, which is equals to 0, 1 minus 2 minus 1 0 0 0, then 1 minus 1 0 minus 1 1, x1, x2, x3, which is equals to 0. Now what we are first we are going to write it in the equation form. Here we can utilize the statistical method. Minus x1 it's equals to 0, then next is x2 minus x3, which is equals to 0, minus x2 plus x3 it's equals to 0. Equation 4, 5 and 6, where I cannot use for solving 5 and 6 because they are similar. So I will move either with the 4 and 5 or 4 and 6. So we will solve 4 and 5. Solving equation 4 and 5. First we have to start with the middle term. First we are going to write the coefficient of x2, x3, then x1. Again we are going to repeat the coefficient of x2. What is the coefficient of x2 here? There is a no, it's a 0, and from the next equation it's a 1, and from here it's equals to 0, and this is minus 1 and minus 1, and here it's a 0, and this is equals to 0 and 1, where x1 it's equals to x2, which is equals to x3, which is equals to some arbitrary constant k. So this is equals to 0 minus 0 0 minus 1, and this is equals to minus 1 minus 0. So what I am going to get here, x1 by 0, x1 by 0, x2 by minus 1, then x3 by minus 1, x1 by 0, x1 by 0 it's equals to x2 by minus 1, x3 by minus 1, it's equals to k. So now what I am going to do, I am going to divide upon the denominator completely with minus 1. So x1 by 0 it's equals to x2 by 1, x3 by 1 it's equals to k. Now my second vector, which is x1, x2, x3 equals to k of 0 1 1. So the two cases are completed. Now I have to move for the third case. The third case value is equals to 4. In case 3, when lambda it's equals to 4, a minus lambda 3I into x3 which is equals to 0, where the value is equals to 1 minus lambda. So 1 minus 4, 0, 0, 0, 3 minus 4 minus 1, 0 minus 1, 3 minus 4, x1, x2, x3 which is equals to 0. It is equals to minus 3, 0, 0, 0, minus 1, minus 1, 0, minus 1, minus 1, x1, x2, x3 which is equals to 0. Now write it into the equation form. Minus 3x1 plus 0x2 plus 0x3 which is equals to 0. Then 0x1 minus x2 minus x3 which is equals to 0. 0x1 minus x2 minus x3 which is equals to 0. 6, already it is over 6, 7, 8 and 9. See, I cannot take 8 and 9 because they are same identical equation, because vector should not be equals to 0. If we are going to consider 8 and 9 equation, the solution is going to be 0. Vector should not be equals to 0. It has at least one value. So we have to clear that whatever the equation we are going to choose, it should not come it's equals to 0. So either I can take 7 and 8 or 7 and 9. Solving equation 7 and 9. So what I am going to get when I am going to solve 7 and 9, again the same procedure. Middle term, last term, first term, again middle term coefficient. So middle term coefficient, it's 0, minus 1, 0, minus 1, minus 3, 0, then 0, minus 1. X1 is equals to, x2 is equals to, x3 is equals to some constant k. So when we are solving, zero, and this is equals to 0, 0, minus 3, 0, oh sorry, it's a 3, and this is equals to 0. So x1 0, it's equals to x2 by minus 3, x3 by 3, it's equals to k. Now I am going to divide with minus 3 because the vector this much big also should not be there. Either the vector values are going to be 1, 2, 3, and 3 is also very rare. So I am going to divide by 3. So x1 by 0, x2 by minus 3 by minus 3, it's equals to x3 by 3 by minus 3, it's equals to k. So x1 by 0, it's equals to x2 by 1, it's equals to x3 by minus 1, it's equals to k. So the third vector x3 which is equals to x1, x2, x3, k of what the values we are having here, 0, 1, minus 1. Now 3 steps are over. Now we have to construct model matrix. Construct model matrix where P is equals to x1, x2, x3. These are your vectors. So P is equals to your first vector. What was the first vector? 1, 0, 0. Then second vector 0, 1, 1. Last vector 0, 1, minus 1. Now after that we have to move for the normalized model matrix. Normalized model matrix. For normalized model matrix, where P is equals to x1 by norm x1, x2 by norm x2, x3 by norm x3, where x1 norm x1, for this one again this will become x1 x2 x3, x1 x2 x3, x1 x2 x3, when we are finding norm x1, which is equals to under root of x1 square plus x2 square plus x3 square, which is equals to 1 whole square plus 0 whole square plus 0 whole square. It's equals to root 1 it's equals to 1. Next, norm x2, which is equals to under root of 0 whole square plus 1 whole square plus 1 whole square, which is equals to root 2. Norm x3, which is equals to under root of 0 whole square plus 1 whole square plus minus 1 whole square, which is equals to root 2. P, it's equals to your norm, your x1. This x1 has to be divided by norm 1. Norm 1 it's equals to 1. So 1, it's 1 0 0 0 1 by root 2 1 by root 2 0 1 by root 2 minus 1 by root 2. In diagonalization, after getting that model matrix, what we were doing, we were going for finding the P inverse, but in the orthogonal transformation, instead of finding the P inverse, we will declare that is P inverse is going to be P transpose. We are saying that I am not going to find what is the value of a P inverse. In place of P inverse, I will take it's equals to P transpose. You are going to do the transpose to this matrix, this P. Further, you have to move with this P. You have to lead the remaining problem with this P only. Normalized model matrix P you have to consider. Therefore, P transpose, which is equals to 1 0 0, then 0 1 by root 2 1 by root 2, this is equals to 0. Then next is 1 by root 2 0 1 by root 2 minus 1 by root 2. Got it. Now from this throughout, I can take 1 by root 2 is equals to common. So it will be going to be easy for me to do the matrix multiplication for P into P transpose. So I will take 1 by root 2 common from here. So the first element will get changed to root 2 0 0. This is equals to 0 1 1 0 1 minus 1. So now my P transpose is equals to 1 by root 2 0 0 0 1 1 0 1 minus 1. Now what I have to do here? I have to find whether it's going to be orthogonal or not, because we have declared here P inverse is equals to P transpose. Now next step we have to check for P transpose, we have orthogonal we have to check. So from this throughout also I can take that is equals to 1 by root 2 I can take common from here. So it's going to be 1 0 0 0 root 2 0, sorry, that is going to be 1 by root 2 of root 2 0 0 0 1 1 0 1 minus 1. Now P into P transpose, I have to go for checking whether it's going to be orthogonal or not. P into P transpose, which is equals to 1 by root 2 of root 2 0 0 0. Next it was what? 1 1 1 1 0 1 minus 1, and 1 by root 2 of root 2 0 0 0 1 1 0 1 minus 1. There is a no change. Now 1 by root 2 1 by root 2, that will give you 1 by 2. 1 by 2 of root 2 0 0 0 1 1 0 1 minus 1 root 2 0 0 0 1 1 0 1 minus 1. rows into columns, rows into columns. So which is equals to 1 by 2 of root 2 into root 2. It's a 2. Then 0 into 0, 0 plus 0. Next it's a 0 plus 0 plus 0. Next 0 plus 0 plus 0. Next 0. 0 plus 0 plus 0, and this goes to 0 plus 1 plus 1, 0 plus 0 plus 0. Next is 0 plus 0 plus 0. Next is equals to 0. Then plus 1 minus 1, 0 plus 1 plus 1. Minus into minus, it's a plus 1. So now 1 by 2 of 2 0 0 0 2 0 0 0 2. Now I am going to take this 2 inside. So I am going to get it's equals to identity matrix. So we got orthogonal matrix. If orthogonal exists, then only we can go for D. Orthogonal, it's got exist. We got P into P transpose is equals to I. Now we'll move for finding the D, where D is equals to P transpose A into P. This D should come, it's equals to eigen value, where P transpose 1 by root 2 of root 2 0 0 0 1 1 0 1 minus 1, then into A, where A is equals to, what was the given matrix? A is equals to 1 0 0 0 3 minus 1 0 minus 1 3. Then 1 by root 2 of root 2 0 0 0 1 1 0 1 minus 1. When we are doing the matrix multiplication, you don't do this into this, it's equals to I, which already proved. No, it's wrong. First finish with AP, then go for the Telangana. Whatever the result you are going to come from AP, that matrix should be multiplied with the Telangana, that is a P transpose. Now this 1 by root 2, 1 by root 2, that will become 1 by 2, that completely I will write here. The next is root 2 0 0 0 1 1 0 1 minus 1, then into 1 0 0 0 3 minus 1 0 minus 1 3. The next is root 2 0 0 0 1 1 0 1 minus 1. Rows into column. First finish off this one. 1 by 2 of root 2 0 0 0 1 1 0 1 minus 1, then into 1 into root 2, it's root 2 0 into 0, 0 plus 0 1 plus 0 plus 0, then 0 plus 0 plus 0, this is equals to 0 plus 0, then this is equals to 0. Next is equals to 0, then 1 into 3, it's a 3 minus 1. Next is equals to 0 plus 3 minus 1 into minus 1 plus 1, then 0 plus 0 plus 0, 0 minus 1 minus 1, then this is equals to plus 3, 0 minus 1 minus 3. 1 by 2 of root 2 0 0 0 1 1 0 1 minus 1 into root 2 1 0 0 2 4 0 2 minus 4. Now you have to do the matrix multiplication for this one. Rows into columns. Rows into columns. So what we are going to get in that case? Root 2 into root 2. Root 2 into root 2, 2 plus 0 plus 0. Next root 2 plus 0 plus 0. Next is equals to 0 plus 0. This will be 0. 0, then plus 0, next this is equals to 0, 0 plus 0, then 0 plus 2 plus 2, 0, then plus 4 minus 4, 0 plus 0 plus 0, 0 plus 2 minus 2, this is equals to 0 plus 4 plus 4. So what matrix we are getting here? 1 by 1 by 2 of 2, 0, 0. Then this is equals to 0, 4, 0, 0, 0, 8. Now take this 2 inside, that is going to give you 1, 0, 0, 0, 4, 4 by 2, 0, 0, 8 by 2. Okay, I'll write here 2 by 2. The 2 we are going to take inside, which is equals to 1, 0, 0, 0, 2, 0, 0, 0, 4. These was only that our eigenvalues. So we got D is equals to eigenvalues, and D, your diagonalization, which is equals to D is equals to eigenvalues, that is equals to 1, 2, 4. So this is known as your canonical form. We have reduced it into the diagonalization. This is known as the orthogonal diagonalization, where quadratic form, which is equals to y transpose D into y, where y is equals to y1, y2, y3. Y transpose is equals to y1, y2, y3. Then D is equals to 1, 0, 0, 0, 2, 0, 0, 0, 4. Then here it is equals to y1, y2, y3, which is equals to y1, y2, y3, rows into columns, y1, 2, y2, 3, y3, which is equals to y1, y1 square plus 2y2 square plus 3y3 square. Now next is what? Orthogonal transformation, that is x is equals to py, where your p is equals to 1 by root 2 of 1 by root 2 of root 2, 0, 0, 0, 1, 1, 0, 1 minus 1, and your y is equals to y1, y2, y3, rows into columns, 1 by root 2 of root 2 y1, next is equals to 0, y2 plus y3, then this is equals to y2 minus y3, where x is equals to x1, x2, x3. It's equals to root 2 y1 by root 2, y2 plus y3 divided by root 2, y2 minus y3 divided by root 2. This and this will get cancelled. x1, which is equals to y1, x2, which is equals to 1 by root 2 of y2 plus y3, x3, it's equals to 1 by root 2 of y2 minus y3. This is known as orthogonal transformation. If we'll go for index, signature and nature, where your eigenvalues is equals to 1, 2, 3. So index is equals to number of positive square terms in canonical form. So number of positive terms in the canonical form, how many we are having? It's equals to 3. 3 positive values we are having. So index is equals to 3. Then signature is equals to number of a positive term minus number of a negative terms. So there is a no negative term. So positive it's equals to 3, negative is equals to 0, which is equals to 3. And nature, where nature is equals to, if all the eigenvalues are positive, then it is known as positive definite. So the nature is equals to positive Definite. Thank you for listening me. If you are having any doubts in this method, leave it in the comment box so that I can clarify the doubt in the next class. Thank you so much for listening me.